What if I told you the next giant leap for humanity isn't just about landing on Mars? It's about transforming space into a second home. Picture this: bustling orbital cities, interplanetary supply chains, and spacecraft that travel faster than ever imagined. These aren't scenes from a distant future. They're the direct result of 22 revolutionary inventions already taking shape in labs and workshops around the world. Right now, engineers and visionaries are cracking problems that once seemed impossible: how to grow food in zero gravity, how to harness the power of the sun for interstellar travel, even how to turn asteroids into cosmic gas stations. The space industry isn't just evolving, it's on the brink of a total reinvention, and today, we're pulling back the curtain on the technologies making it happen. Think about how air travel changed the world in the 20th century, shrinking continents, connecting cultures, rewriting economies. Now, imagine that same level of disruption, but for the cosmos. The inventions we're about to explore aren't just incremental upgrades. They're keys that will unlock entirely new chapters in human history. Some will solve mysteries that have puzzled scientists for decades, like how to protect astronauts from deep space radiation. Others will turn science fiction into reality, like robotic swarms that build structures on the moon or propulsion systems that slash travel time to Saturn's moons. What ties them all together? They're not distant dreams. Prototypes exist, tests are underway, the future is closer than you think. This isn't just a story of gadgets and machinery. It's about the human spirit's relentless drive to push boundaries. Every invention on this list represents countless hours of collaboration, failure, and breakthroughs. They're proof that when we aim for the stars, we don't just reach new destinations, we transform life back on Earth. The same technologies designed for space could revolutionize medicine, energy, and even how we tackle climate change. So whether you're a space enthusiast or just curious about where humanity is headed next, you're about to witness the blueprints for a cosmic revolution. The countdown starts now. Let's dive into the 22 visionary inventions set to disrupt the space industry forever and change our place in the universe. Lightweight solar sails might sound like something straight out of a sci-fi novel, but they're very real, and they're poised to upend how we think about space travel. Unlike traditional rockets that rely on burning massive amounts of fuel, these ultra-thin, reflective sails harness the gentle but constant pressure of sunlight itself for propulsion. Picture a spacecraft unfurling a shimmering sail the size of a football field, catching photons like a boat catching wind. Each tiny push from sunlight adds up over time, allowing these vessels to reach incredible speeds without carrying heavy fuel tanks. NASA NEA Scout mission, set to hitch a ride on the Artemis program, will test this very concept by journeying to a near-Earth asteroid. No engines, no explosions, just the silent power of sunlight. But the real game-changer lies in the long-term potential. Solar sails could make missions to the outer solar system, or even neighboring stars, far more feasible. Traditional fuel limits how far and how long we can explore, but a sail-powered craft could theoretically keep accelerating for years, reaching speeds that chemical rockets can't match. Imagine a fleet of these sails drifting toward Alpha Centauri, carrying tiny probes to study distant worlds, or consider their role closer to home, monitoring solar weather, mapping asteroids, or even serving as interstellar messaging relays. The best part: once deployed, they require no refueling, slashing mission costs and enabling ventures that would have been too expensive or risky with conventional propulsion. What makes this invention truly disruptive isn't just the technology itself. It's the mindset shift it represents. For decades, space travel has been bound by the limitations of fuel. Solar sails break that dependency, turning an abundant, free resource, sunlight, into an engine. Innovations like this remind us that sometimes the most radical solutions are also the most elegant. While they won't replace rockets entirely, sails need sunlight to work. After all, they open a new lane in the cosmic transportation network, one where efficiency and sustainability take center stage. The future of exploration might just glide silently on beams of light. Now imagine cutting the journey to Mars in half, not with bigger fuel tanks or more powerful engines, but by harnessing the controlled fury of atomic energy. Nuclear thermal propulsion isn't just an upgrade to traditional rockets. It's a complete reimagining of how we push spacecraft through the void. Here's how it works. Instead of burning chemical fuels, a compact nuclear reactor heats liquid hydrogen to extreme temperatures, blasting it out as superheated plasma to generate thrust. The result, a system that packs twice the efficiency of conventional engines, slashing travel times and rewriting the rulebook for deep space missions. NASA and DARPA aren't just theorizing, they're building. The Draco program, short for Demonstration Rocket for Agile Cislunar Operations, aims to test a nuclear thermal spacecraft in orbit as early as 2027. Picture a future where astronauts bound for Mars spend months, not years, in transit. That's more than a convenience, it's a survival advantage. Every extra day in deep space means more exposure to cosmic radiation, a silent threat that could derail humanity's interplanetary ambitions. Faster trips reduce those risks dramatically, while also preserving supplies and crew morale. But the real brilliance of this technology lies in its versatility. Unlike solar sails, which depend on sunlight, nuclear thermal propulsion works anywhere, whether you're racing toward Jupiter or navigating the shadowy reaches of the outer solar system. And while the word nuclear might sound alarming, these systems are designed with fail-safes to prevent accidents. The reactor only activates in space, remaining inert during launch to avoid any risk of Earth-based contamination. What makes this invention a game-changer isn't just speed, it's sustainability. Chemical rockets guzzle fuel, limiting payloads and mission flexibility. Nuclear thermal engines, by contrast, stretch their propellant farther, enabling heavier cargo loads or even round-trip missions without refueling. Imagine a world where Mars isn't a one-way destination, but a regular stop on an expanding interplanetary trade route. The implications ripple beyond exploration. Quicker supply runs to lunar bases, rapid response scientific missions to study passing comets, even the potential for crewed flights to the asteroid belt. This isn't just about getting there faster. It's about staying longer, going farther, and doing more once we arrive. While solar sails offer elegance, nuclear thermal propulsion delivers raw capability, proving that humanity's next era in space might be powered by the atom. The race to Mars just found its most promising shortcut. Packing for a trip to Mars isn't like stuffing a suitcase for a beach vacation. Every extra gram hauled from Earth comes with astronomical costs. That's where in-situ resource utilization flips the script entirely. Instead of shipping every drop of water and every breath of air across millions of miles, ISRO turns alien landscapes into cosmic hardware stores. Picture a lunar outpost where rovers bake sunlight into oxygen by splitting iron-rich moon dust, or a Martian factory that 3D prints spare parts from rust-colored soil. These aren't just clever tricks, they're the foundation for making humanity multiplanetary. The genius of ISRO lies in its simplicity. Work with what's already there. Take water, for instance. Shadows at the moon's poles hide vast ice deposits. while certain Martian minerals contain water molecules locked in their structure. Specialized processors can heat or chemically treat these materials to extract life-sustaining H2O, not just for drinking, but for splitting into hydrogen and oxygen to make rocket fuel. Suddenly, a lunar crater becomes both a canteen and a gas station for deeper space missions. Companies like SpaceX see this as the ultimate pit stop strategy. Their Starship could refuel on Mars using local resources instead of hauling Earth-made propellant for the return trip, effectively cutting mission mass in half. But the real magic happens when you look beyond basics. Mars' iron-rich regolith could feed autonomous smelters, producing construction beams for habitats. Lunar anorthosite contains aluminum perfect for printing solar panels. Even the carbon dioxide in Mars' atmosphere becomes raw material. Imagine microbes engineered to transform CO2 into plastics or nutrients. Blue Origin's Blue Alchemist program is already prototyping solar-powered systems that produce solar cells and wire solely from moon dust. No Earth imports needed. What makes ISRO truly revolutionary isn't just the technology, it's the economic ripple effect. Shipping a single bottle of water to orbit costs thousands today. Manufacturing it on-site, pennies by comparison. This shifts space exploration from a government-funded sprint to a sustainable enterprise where private companies can profit from supplying orbital depots or leasing refinery equipment. The first lunar mining startups could mirror Earth's 19th century gold rush, but with 3D printed drills instead of pickaxes. Critics argue these systems add complexity. Why not just send everything pre-packed? But history proves self-sufficiency wins long games. Early Antarctic explorers perished when supply ships failed. Modern bases thrive by generating their own power and recycling waste. ISRO offers that same leap for space, transforming dead worlds into workshops where humanity can build, experiment, and stay indefinitely. The next giant leap isn't just planting flags, it's learning to live off the extraterrestrial land. What if we could ditch the idea of launching fully assembled spacecraft from Earth and instead print them directly in orbit? Space-based 3D printing is turning that vision into reality, and it's about to rewrite the economics of space construction. Traditional methods require painstakingly building components on Earth, then cramming them into rockets where every square inch costs a fortune. But with orbital 3D printers, we could manufacture everything from satellite parts to entire space station modules right where they're needed. No bulky payloads, no size restrictions from launch fairings. Startups like Relativity Space are leading the charge, developing massive printers that can fabricate rockets layer by layer using metal alloys. Their Terran R rocket, slated for debut in 2026, will be almost entirely 3D printed, not just small components, but the entire fuselage and engines. Now imagine scaling that concept for use in microgravity. Without Earth's gravity dragging down molten materials, printers could create ultra-precise structures that would collapse under their own weight back home. Delicate latticework for solar arrays, sprawling antenna dishes, even habitats with intricate internal scaffolding, all become feasible when you're building where they'll be used. The real breakthrough isn't just about saving money, though that's massive. Launch costs currently run around $10,000 per kilogram sent to orbit. Printing even half a satellite's mass in space could slash budgets by millions. It's about unlocking designs we've never dared attempt. Think of spiderweb thin space telescope mirrors spanning hundreds of feet, or modular space stations that grow organically as new sections are printed on demand. NASA Archinaut project has already tested this in vacuum chambers, with robotic arms assembling printed parts into functional spacecraft skeletons. But perhaps the most exciting twist is how microgravity changes the materials themselves. Earth-bound 3D printing struggles with layer adhesion and thermal stresses. In space, molten metals cool uniformly, creating stronger, more consistent bonds. Researchers are experimenting with lunar and Martian dust as printing feedstock, meaning future moon bases might literally rise from the ground up using local dirt. The European Space Agency has even explored printing entire satellite components from recycled space junk, turning orbital debris into valuable raw material. This isn't just another manufacturing upgrade. It's a paradigm shift that could democratize access to orbit. Smaller nations or companies could upload digital blueprints to shared orbital factories, bypassing the need for massive terrestrial infrastructure. Emergency satellite replacements could be printed within days after solar storms or collisions. And for deep space missions, imagine sending a compact printer ahead to Mars that churns out landing pads and radiation shelters before astronauts ever leave Earth. The age of disposable rockets and one-time use hardware may soon give way to a more elegant era where space builds itself. Floating effortlessly might look fun in videos from the International Space Station, but our bodies pay a steep price for life without gravity. Muscles wither, bones lose density at 10 times the rate of osteoporosis, and even vision degrades over time. NASA calls it spaceflight-associated neuroocular syndrome. These aren't just hurdles for Mars missions, they're deal-breakers for any dream of permanent space settlements. That's where artificial gravity steps in, not as sci-fi magic, but as straightforward physics. Spin a structure fast enough, and centrifugal force pins objects to the inside of its walls, creating the illusion of gravity. The concept dates back to rocket pioneer Wernher von Braun's sketches in the 1950s, but today's materials and engineering are finally making it practical. Take the Stanford Torus, a donut-shaped habitat designed during NASA's 1975 summer study. At just under 1 mile in diameter, rotating at 1 revolution per minute, its outer rim would simulate Earth gravity, perfect for maintaining bone strength while eliminating the disorientation problems of faster spins. Modern iterations could be even smarter. Picture segmented floors that adjust rotation speed based on purpose, labs at lunar gravity for specialized research, living quarters at full Earth gravity, and transitional zones helping astronauts adapt. Companies like Gravitics are already prototyping modular spinning sections for future space stations, where each ring's rotation can be fine-tuned like gears in a cosmic clockwork. But the real showstopper is the O'Neill cylinder, a vision so grand it redefines what space habitats could be. 2 counter-rotating tubes, each 4 miles wide and 20 miles long, spin to create Earth-like conditions along their inner surfaces. Sunlight streams through massive mirrors, while the entire structure floats in stable Lagrangian points between Earth and the Moon. What sounds like fantasy is inching toward plausibility thanks to ultra-lightweight nanomaterials. Graphene-reinforced composites could provide the strength needed for such colossal structures without requiring unobtainium materials. Recent experiments with self-healing polymers even address micrometeorite risks. Imagine walls that seal punctures like a scab forming on skin. The health benefits are just the start. Artificial gravity enables technologies we take for granted on Earth, but that fail in microgravity. Think ordinary plumbing, convection-based cooling, even simple showers. More profoundly, it solves the reproduction question. We have no data on mammalian gestation in 0G, and ethical concerns make experiments unlikely. A spinning habitat removes the uncertainty, offering future space families the same developmental conditions Earth's biology expects. Agriculture thrives too, roots grow downward, water drains properly, and pollinators like bees can navigate normally. Critics argue the energy costs are prohibitive, but momentum is free in space. Once set spinning, a habitat's angular momentum persists indefinitely with minimal power for corrections. Solar-powered electromagnetic bearings could replace friction-heavy mechanical ones, making the systems nearly maintenance-free. Smaller-scale prototypes are already on drawing boards, from Gateway Foundation's Voyager station, a hotel concept with partial gravity, to China's Chang'e program's rumored spinning lab module. This isn't just about comfort, it's about rewriting the rules of spacefaring civilization. Without gravity, humanity remains cosmic tourists. With it, we become galactic citizens capable of raising generations among the stars. The technology exists not in some distant century, but within our grasp, waiting only for the will to build it. Imagine sending a message to Mars with absolute certainty that no one could intercept or alter it, not just encrypted, but fundamentally unhackable. That's the promise of quantum communication networks, where the bizarre rules of quantum mechanics replace the vulnerabilities of traditional radio signals. At the heart of this revolution lies quantum entanglement, a phenomenon Einstein famously called spooky action at a distance. When two particles become entangled, their properties link instantaneously, no matter how far apart they are. Change one and the other changes too, even if it's light years away. This isn't just theoretical. China's Mishi satellite has already proven it works, beaming entangled photons between ground stations over 700 miles apart while maintaining their quantum connection. The implications for space exploration are staggering. Current deep space communication relies on radio waves which weaken over distance and take minutes or hours to travel between planets. Worse, they're susceptible to eavesdropping or jamming. Quantum key distribution sidesteps these issues entirely. Here's how: entangled particles generate encryption keys that exist only when observed. Any attempt to spy on the transmission disrupts the quantum state, alerting both sender and receiver to tampering. It's like sealing a letter with wax that shatters if touched, except the wax is a fundamental law of physics. Future Mars bases could use this to receive medical data, navigation updates, or classified research with ironclad security. But the real breakthrough isn't just security, it's speed. While quantum signals don't break light speed, sci-fi fans, they eliminate the need for complex error-checking protocols that slow down conventional transmissions. Picture mission control sending real-time adjustments to a rover on Europa without worrying about signal degradation across 500 million miles. Or astronauts video calling Earth from Titan with zero lag, their quantum-linked devices bypassing the usual delays of interplanetary internet. Scalability is the next frontier. Mishi was a single satellite, but constellations of quantum relays could form an interstellar backbone. The European Space Agency's Quantum Communications Infrastructure Initiative aims to deploy such a network by 2030, linking Earth and lunar assets first. Private ventures like Quantum X have proposed modular satellites that generate and distribute entangled photons like cosmic switchboards. Pair these with ground-based quantum repeaters already in development at labs from Delft to MIT, and suddenly, the entire solar system gets wrapped in an ultra-secure web. Critics highlight the challenges. Maintaining entanglement over astronomical distances requires staggering precision, and cosmic radiation can disrupt fragile quantum states. Yet recent advances in error correction and photon shielding are turning hurdles into solvable engineering problems. NASA's a Deep Space Quantum Link project is testing hardened quantum transceivers that could survive decades near Jupiter's radiation belts. Meanwhile, Japan's National Institute of Information and Communications Technology has prototyped quantum memory, devices that store entangled states long enough to bridge planetary orbits. This isn't just about better walkie-talkies for astronauts. Quantum networks could sync atomic clocks across planets, enabling GPS-like navigation anywhere in the solar system. They might even connect future quantum computers on Earth and Mars into a single, planet-spanning superprocessor. The technology echoes the telegraph's impact in the 19th century, but instead of shrinking continents, it's knitting together worlds. As private and national programs race to deploy these systems, one truth becomes clear. The future of space communication won't rely on stronger signals, but on the unbreakable whispers of entangled particles. Picture a swarm of robotic bees buzzing around a damaged satellite, each no larger than a microwave yet packed with precision tools and artificial intelligence. These aren't sci-fi drones, they're the next generation of orbital repair crews, and they're about to revolutionize how we maintain infrastructure in space. Autonomous space drones solve a critical problem. Right now, fixing anything beyond Earth's atmosphere requires either astronomically expensive human spacewalks or writing off billion-dollar equipment as junk. Companies like Astroscale and Northrop Grumman are already testing prototypes that could turn this paradigm on its head. Their secret sauce, combining nimble robotics with AI capable of making split-second decisions without waiting for signals from ground control, which can take minutes or hours to reach distant spacecraft. Take the ELSA-D mission, which successfully demonstrated how a chaser drone could autonomously locate, dock with, and to orbit a defunct satellite, all while navigating the chaotic ballet of orbital mechanics. The implications stretch far beyond cleanup. Imagine a fleet of these drones performing routine maintenance on the James Webb Space Telescope, delicately adjusting mirror segments or replacing degraded sunshield layers. Or consider their role in constructing future space stations. Instead of astronauts piecing together modules during dangerous extravehicular activities, swarms of drones could assemble entire frameworks like cosmic worker ants, guided by shared blueprints and real-time LiDAR mapping. The true game-changer lies in their collective intelligence. Individual drones might specialize, some equipped with welding torches for structural repairs, others with spectrometers to diagnose fuel leaks. But when networked, they become more than the sum of their parts. Researchers at the University of Surrey's Space Centre have modeled hive-mind algorithms where drones share sensor data to triangulate faults invisible to any single unit. It's akin to how schools of fish or flocks of birds move as one entity, except these robotic swarms could calibrate a satellite's antenna array or detangle a snagged solar panel with millimeter precision. What makes this invention particularly urgent is the ticking time bomb of space debris. Over 30,000 trackable objects currently whiz around Earth at 17,000 miles per hour, each a potential bullet capable of crippling critical infrastructure. Traditional solutions like nets or harpoons risk creating more fragments, but autonomous drones offer a surgical approach. Astroscale's upcoming ADRAS-J mission will showcase how AI can analyze a derelict rocket's tumble pattern, then plot a safe approach to attach stabilizing thrusters. Future iterations might carry compact lasers to vaporize tiny debris or deploy adhesive foams to capture shrapnel. The economics are just as compelling. Sending humans for repairs costs roughly $100 million per spacewalk when accounting for training, insurance, and vehicle support. A drone swarm, once developed, could work indefinitely for marginal operating costs. Startups like OrbitFab are even prototyping orbital gas stations where maintenance drones could refuel satellites, extending their lifespans by years. This isn't just about saving money, it's about preserving assets too valuable to lose, like climate monitoring satellites or global internet constellations. Critics worry about autonomy gone awry. What if a drone misidentifies an active satellite as debris? That's where fail-safes come in. Current systems use multi-layer verification. Only after cross-checking orbital databases, visual signatures, and direct owner confirmation will they proceed with interventions. The same machine learning that enables independence also allows these drones to recognize "do not touch" scenarios, much like self-driving cars identify emergency vehicles. Looking ahead, the technology could birth entirely new space industries. Imagine asteroid mining operations where drone swarms prospect and extract resources while supervised by a single human operator. Or deep space missions where self-repairing probe clusters navigate the asteroid belt, patching each other's micrometeorite damage en route to Jupiter. The International Space Station has already tested early versions with its Astrobee free-flying robots, proving the concept in microgravity. This isn't just about replacing human hands, it's about augmenting our reach. Astronauts will always be essential for exploration, but for the dirty, dangerous, and repetitive tasks, that's where our robotic partners shine. As launch costs plummet and AI matures, the decade ahead could see thousands of these drones transforming orbit from a graveyard of dead satellites into a dynamic workshop where infrastructure builds, maintains, and even upgrades itself. The age of disposable spacecraft is ending, and the era of eternal orbital services has begun. Forget everything you know about roaring rocket engines and billowing smoke. The future of propulsion is nearly silent, glowing with an eerie blue light. Plasma-based thrusters represent one of the most efficient ways to move through space, trading brute force for precision and endurance. Unlike chemical rockets that guzzle fuel in violent explosions, these systems work more like cosmic sailboats, harnessing electric fields to gently but relentlessly push spacecraft forward. Here's the magic: they ionize inert gases like xenon, stripping electrons to create superheated plasma, then use electromagnetic fields to hurl those charged particles out the back at speeds exceeding 110,000 miles per hour. The result, 10 times more efficient than traditional engines, with some prototypes achieving the equivalent of highway gas mileage in space, 90 miles per gallon, but for the cosmos. NASA's Next Sea thruster exemplifies this quiet revolution, currently powering the DART mission that famously nudged an asteroid off course. It generates just enough thrust to hold a sheet of paper on your palm. But in the frictionless void of space, that whisper of acceleration adds up. Over months or years, it can propel probes faster than any chemical rocket capable of leaving Earth's gravity. The European Space Agency's dual-stage 4-grid system takes it further, stacking multiple acceleration stages to squeeze even more speed from each precious atom of fuel. Imagine a car that could drive from New York to Los Angeles on a thimble of gasoline. That's the level of efficiency we're talking about. What makes plasma propulsion truly disruptive isn't just fuel savings, it's mission flexibility. Chemical rockets follow a go-fast-now approach, burning most fuel in minutes to escape Earth, then coasting for years. Plasma thrusters operate continuously, allowing mid-course corrections impossible with conventional systems. A Mars-bound ship could adjust its trajectory weekly to avoid solar storms or optimize arrival angles. Deep space probes could tour multiple asteroids or moons in a single mission, rewriting textbooks on planetary science. Private company Ad Astra's Vasima engine, short for Variable Specific Impulse Magnetoplasma rocket, even promises throttle control, letting spacecraft switch between high-efficiency cruising and bursts of speed when needed. The real game-changer lies beyond our solar system. While chemical rockets might never reach another star within human lifetimes, scaled-up plasma drives could. Breakthrough Starshot, the ambitious plan to send probes to Alpha Centauri, considers plasma propulsion as a potential secondary system after light sails. Closer to home, these engines could maintain cycler stations, permanent habitats shuttling between Earth and Mars on fixed orbital paths, requiring only minor thrust adjustments. NASA's Lunar Gateway Station may soon test this concept with a plasma-powered orbital tug, proving the tech's reliability for crewed missions. Material science breakthroughs are removing remaining limitations. Traditional ion thrusters erode their own components over time, but new tungsten alloys and self-healing ceramics could extend operational lifetimes beyond a decade. Compact nuclear reactors like those in development by Ultra-Safe Nuclear Corporation could provide the megawatts of electricity these systems crave without relying on oversized solar panels. Even the fuel equation is evolving. Startups like Phase 4 are replacing expensive xenon with cheaper argon or even atmospheric gases scooped mid-flight from planetary atmospheres. Critics point to the slow initial acceleration it took NASA's Dawn spacecraft 4 days to go from 0 to 60 miles per hour, but in space racing, patience pays off. While chemical rockets win sprints, plasma thrusters dominate marathons, eventually overtaking their fuel-guzzling cousins. The coming decade will see this technology transition from niche science missions to mainstream use, with companies like SpaceX and Blue Origin reportedly developing hybrid systems combining chemical boosters with plasma upper stages. This isn't just another engine upgrade, it's a fundamental shift in how humanity moves through space. By trading explosive power for relentless efficiency, plasma propulsion unlocks missions that were previously science fiction. Decade-long tours of Jupiter's icy moons, sample returns from Pluto, even manned orbital factories between Earth and Venus. The age of cosmic steamboats is ending, and the era of electric starships has begun. Spacecraft hulls have always been defenseless against the cosmic sandblaster of micrometeorites until now. Self-healing materials are turning brittle metal shells into something more like living skin, capable of sealing punctures automatically without human intervention. Picture a lunar habitat struck by a grain-sized meteor traveling at 30,000 miles per hour. Instead of decompression alarms triggering emergency protocols, the wall simply heals. Tiny vascular networks within specially engineered polymers ooze sealant into breaches, hardening within seconds under ultraviolet light. The European Space Agency's Bionic project has already demonstrated this with panels that recover 80% of their original strength after impact, like a scab forming in zero gravity. But polymers are just the beginning. Imagine metal that welds itself back together. Researchers at the University of Michigan are developing alloys laced with microscopic capsules of liquid gallium. When cracks form, these capsules rupture, releasing gallium that diffuses into the damaged area. Since gallium bonds with most structural metals at room temperature, it essentially performs autonomous cold welding. Tests show these materials can completely close millimeter-scale fissures caused by radiation fatigue, a common headache for long-duration satellites. NASA's upcoming Moon to Mars mission architecture reportedly includes these alloys in critical components, potentially extending spacecraft operational lifetimes from years to decades. The biological inspiration behind these innovations is just as fascinating as the tech itself. Some materials mimic how human blood platelets activate clotting mechanisms, using embedded microspheres that rupture under stress to release healing agents. Others take cues from plant biology, like the self-sealing latex in rubber trees. The most advanced versions even feature hybrid systems, ceramic matrices that regenerate like bone, combined with polymer tendons that contract to pull cracks closed. Japan's Aerospace Exploration Agency has prototyped a lunar rover wheel using this approach, capable of repairing tread damage from sharp regolith simply by parking in sunlight to activate thermally responsive healing compounds. Radiation resistance adds another layer of genius. Traditional materials degrade when cosmic rays knock atoms out of place, creating microscopic voids that weaken structures over time. Self-healing alternatives counteract this through what scientists call vacancy filling. Certain metal alloys, particularly those with nickel-titanium compositions, naturally redistribute their atoms to fill these voids when heated, something that happens passively in space due to temperature swings between sunlight and shadow. Engineers at SpaceX have hinted at using this property in next-gen Starship hulls, where the mere act of orbiting between Earth's day and night sides could theoretically erase years' worth of radiation damage. The economic implications are staggering. Consider the International Space Station, which spends approximately $4 billion annually on maintenance, much of it addressing micrometeorite damage. A habitat built with self-healing polymers could slash those costs while eliminating life-threatening risks from sudden decompression. Private stations like Orbital Reef plan to incorporate these materials from their first modules, essentially giving their structures immune systems against space's relentless abrasion. What makes this invention truly disruptive isn't just durability, it's enabling missions we've never dared attempt. Imagine probes diving into Saturn's radiation belts or enduring Mercury's scorching daysides without shielding failures. Or consider generation ships where hull integrity must last centuries without replacement. Even mundane components benefit. Self-sealing gaskets could prevent the kind of slow oxygen leaks that derailed Russia's early space stations. When every gram of spare parts costs thousands to launch, materials that fix themselves become the ultimate mass-saving technology. While challenges remain, particularly in balancing healing speed with structural strength, the progress is accelerating faster than cracks can form. Recent breakthroughs include 3D printed metamaterials that alter their molecular arrangement in response to damage, and graphene-doped ceramics that knit back together using ambient cosmic radiation as an energy source. The message to future astronauts is clear. Your spacecraft won't just withstand the harshness of space, it will actively fight back. Climbing to space might sound like fantasy, but the physics behind space elevators checks out if we can crack one monumental challenge. Imagine a ribbon stronger than steel stretching 22,000 miles into the sky, anchored to Earth's equator and balanced by a counterweight beyond geostationary orbit. Elevator cars powered by lasers or electromagnetic pulses could glide up this tether, hauling cargo and passengers to orbit for a fraction of today's rocket costs. The math is tantalizing. While launching a kilogram on a Falcon 9 costs around $2,000, a space elevator could slash that to mere dollars, potentially democratizing access to orbit like railroads opened the American frontier. Carbon nanotubes hold the key. These microscopic cylinders of carbon atoms boast a tensile strength 100 times greater than steel at just a fraction of the weight. Early experiments by institutions like Cambridge University have produced strands centimeters long, but scaling to the thousands of kilometers needed demands breakthroughs in manufacturing purity and defect prevention. Japan's Obayashi Corporation aims to overcome this by 2050, planning a lunar elevator first where weaker materials suffice due to lower gravity. Their prototype involves robotic climbers scaling a carbon nanotube cable stretched from the Moon's surface to Lagrange points, a proving ground for Earth's far more ambitious version. The engineering hurdles read like a sci-fi checklist. A terrestrial elevator would face hurricane-force winds in the lower atmosphere. atomic oxygen erosion in the upper layers, and space debris strikes along its entire length. Proposed solutions range from active stabilization using magnetic levitation to segmented tethers that can isolate damage like a submarine's watertight compartments. Even the anchor station poses challenges. Floating platforms in the equatorial Pacific would need to dynamically adjust for storms while handling the colossal tension of a structure that weighs millions of tons. Yet the payoff justifies the obsession. Unlike rockets that burn fuel fighting gravity, elevators would use Earth's rotation as their engine, trading time for efficiency. A week-long climb might seem slow until you consider the cargo capacity. A single elevator could theoretically lift thousands of tons annually, enough to construct entire space stations in orbit from prefabricated modules. Asteroid mining operations would flip from pipe dreams to viable businesses when raw materials can be shipped surface-ward for pennies per pound. Tourism could blossom with hotels at various altitudes offering everything from zero-G novelty stays to panoramic views rivaling the ISS. Safety concerns demand attention. A snapped tether wouldn't simply fall. The upper portion might whip outward into space while the lower half wraps around the planet like a deadly lasso. Engineers propose fail-safes like explosive bolts to sever the cable into harmless fragments if instability is detected. Others suggest building initial elevators on remote mountains like Chimborazo in Ecuador, whose peak sits farthest from Earth's center, reducing required cable length and collateral risk. The ripple effects extend beyond transportation. Elevator infrastructure could spark an energy revolution. Solar power satellites assembled in orbit might beam gigawatts to ground stations via the tether itself. Climate science would leap forward with ultra-affordable atmospheric sensors deployed along the cable's length, creating the most detailed model of Earth's weather systems ever conceived. Even global internet coverage could be revolutionized by relay stations spaced along the route, eliminating dead zones without thousands of satellites. While skeptics argue the concept relies on materials that don't yet exist at scale, history reminds us that impossibility often precedes innovation. The Panama Canal was once dismissed as a fool's errand until engineering caught up with ambition. Whether space elevators arrive in 50 years or 100, their promise is too transformative to ignore, a silent highway to the stars that could render rocket launches as obsolete as steamships crossing the Atlantic. The race to build the first one isn't just about reaching orbit. It's about redefining how humanity interacts with the cosmos itself. Fusion-powered rockets sound like something ripped from the pages of a sci-fi novel, but they represent one of the most promising and challenging breakthroughs on the horizon for space travel. Unlike conventional rockets that burn chemical fuel or even nuclear thermal systems that split atoms, these engines would harness the same process that powers stars, fusing lightweight atomic nuclei to release colossal amounts of energy. The numbers are staggering. A single gram of fusion fuel could theoretically deliver the equivalent energy of 8 tons of rocket propellant, slashing travel time to Mars from months to weeks and making Jupiter's moons reachable in under a year. Helion Energy's approach exemplifies the audacity of this pursuit. Their compact reactor design skips the traditional tokamak donut shape in favor of a linear system that pulses 30 times per second, squeezing hydrogen isotopes with magnetic fields until they fuse into helium and releasing energy directly as electricity. No steam turbines, no radioactive waste, just raw propulsion power. Late-stage tests have already achieved plasma temperatures of 100 million degrees Celsius, hotter than the sun's core. Partnering with NASA, Helion aims to demonstrate a space-ready prototype by 2030, potentially integrating their reactor with plasma thrusters for unprecedented efficiency. TA Technologies takes a different path with their hydrogen-boron fusion model. While most reactors target deuterium-tritium fusion, which produces problematic neutrons, TA's system fuses hydrogen with boron-11, yielding only stable helium and energy in the form of charged particles. These can be directed by magnetic nozzles to create thrust, eliminating the need for heavy radiation shielding. Their Norman reactor has sustained plasma for milliseconds at a time, a blink by Earth standards, but a leap for controlled fusion. The real win, hydrogen-boron fuel, is abundant and non-radioactive, mined from seawater and borax deposits rather than rare isotopes. The engineering hurdles remain daunting. Containing star core temperatures without melting the reactor walls requires materials that don't yet exist outside lab experiments. Lockheed Martin's Skunk Works once proposed solving this with high-temperature superconductors and self-stabilizing plasma configurations, but their progress remains classified. Meanwhile, startups like Zap Energy are testing sheared flow stabilization using plasma's own motion to prevent disruptive instabilities that have plagued fusion research for decades. What makes fusion propulsion revolutionary isn't just speed, it's stamina. Chemical rockets exhaust their fuel in minutes. Fusion engines could theoretically run for years on a few kilos of fuel, enabling missions that redefine exploration. Picture a probe arriving at Saturn not as a battered relic running on fumes, but as a fully operational craft with decades of power left to tour every moon. Or consider generation ships where fusion reactors double as power plants for onboard ecosystems, sustaining crews across interstellar distances. Critics argue the timeline is perpetually 30 years away, but the landscape is shifting. Private investment now surpasses government funding in fusion research, accelerating innovation through competition. Microsoft has already pre-ordered electricity from Helian's first commercial reactor, a vote of confidence that the technology is nearing viability. For space applications, even partial success could be transformative. Hybrid systems might use fusion to preheat propellant for nuclear thermal rockets, boosting efficiency while buying time to solve containment challenges. The ultimate prize, interstellar capability. While light sails and antimatter remain speculative for crewed travel, fusion offers a plausible path to nearby stars. Project Daedalus, the British Interplanetary Society's 1970s Starship design, relied on inertial confinement fusion, detonating pellets with lasers to create pulsed thrust. Modern iterations could achieve 10% light speed, reaching Alpha Centauri in a human lifetime. This isn't just about building better rockets, it's about rewriting the fundamental economics of spaceflight. When energy becomes nearly free and propulsion systems last decades, the solar system transforms from a series of distant outposts into a connected neighborhood. Lunar factories, Martian cities, and asteroid mines cease being isolated ventures and become nodes in an interplanetary network, all powered by miniature stars we carry with us. The dream isn't just to reach the cosmos, but to take a piece of its fire along for the ride. Breathing easy in space isn't just about carrying enough oxygen tanks. It's about creating an ecosystem that regenerates itself. Bio-regenerative life support systems turn spacecraft into living, breathing environments where every exhale becomes fuel and every scrap of waste transforms back into nutrients. Picture a Mars-bound habitat where walls bloom with vertically farmed wheat, algae tanks scrub carbon dioxide into fresh oxygen, and microbial reactors break down sweat into drinkable water. This isn't just recycling. It's biomimicry at its finest, replicating Earth's own life support systems on a spacecraft scale. NASA's Advanced Plant Habitat aboard the International Space Station has already grown 3 generations of Arabidopsis plants in microgravity, proving crops can thrive from seed to harvest without Earth's gravity. Meanwhile, Europe's SSA project, short for Microecological Life Support System, Alternative, operates like a cosmic stomach, using spirulina algae and bacteria to convert astronaut waste into protein-rich food and purified water. The magic lies in closing the loop. Traditional life support relies on resupply missions or bulky chemical processes that eventually wear out. A bio-regenerative system, by contrast, leverages living organisms that grow and adapt. Take water recovery. Current ISS systems reclaim about 90% of water through distillation and filtration, but the remaining 10% slips away as humidity or urine residue. Enter the University of Arizona's lunar greenhouse prototype, where transpiration from potato plants condenses into clean water on leaf surfaces, no energy-intensive machinery required. Or consider how researchers at the Kennedy Space Center engineered a strain of duckweed that doubles as both air purifier and emergency food source, producing oxygen while packing more protein per acre than soybeans. Long-duration missions demand this level of efficiency. A 4-person crew bound for Mars would need an estimated 12 tons of water and 3 tons of food for a 3-year round trip if relying solely on stored supplies. Bio-regenerative systems could slash that payload by 80% or more. China's Lunar Palace 1 experiment demonstrated this in a terrestrial analog, where volunteers lived for 370 days in a sealed habitat powered entirely by wheat, vegetables, and mealworms they cultivated themselves. The psychological benefits are equally profound. Studies show astronauts tending plants exhibit lower stress levels and better cognitive function, turning greenhouse modules into both pantries and therapy rooms. The real breakthrough comes when these systems scale beyond basic survival. Imagine Martian greenhouses growing not just kale but strawberries, coffee, or even hardwood trees for construction materials. Synthetic biology startups like Ginkgo Bioworks are engineering microbes to produce medicines or bioplastics from astronaut waste, potentially enabling off-world manufacturing. ESA's recent experiments with biofabrication have even grown fungal mycelium into lightweight furniture, substitutes meaning future bases might cultivate their own chairs and tables rather than shipping them from Earth. Challenges remain, of course. Balancing ecosystems in confined spaces requires exquisite precision. An overgrowth of algae could consume too much oxygen, while a crop failure might cascade through the food chain. That's why next-gen systems incorporate AI monitoring like the Bio-Intelligent Habitat being tested by Lockheed Martin, which uses machine learning to predict and correct imbalances before they endanger crews. Radiation-resistant genetically modified crops are another frontier, with scientists editing plant DNA to withstand cosmic rays that would wither conventional varieties. What makes this invention truly transformative isn't just the technology, it's the philosophy shift. We're moving from seeing spacecraft as sterile machines to treating them as synthetic biomess where humans coexist with thousands of other organisms. The same principles could one day terraform entire worlds, seeding Mars with engineered ecosystems that precondition its atmosphere for human settlement. For now, these closed-loop systems offer something equally revolutionary: the promise that when we leave Earth, we won't just bring supplies, we'll bring a piece of our planet's beating, breathing heart along for the journey. Asteroid mining robots might sound like the plot of a Hollywood blockbuster, but these autonomous prospectors are already in development, and they could kickstart the first trillion-dollar industry beyond Earth. Picture a swarm of drones no larger than refrigerators, descending onto a carbon-rich asteroid with diamond-tipped drills and miniature refineries. Their mission, extract precious metals like platinum and gold, along with something even more valuable in space water. Companies like Planetary Resources, backed by Google's Larry Page, have spent a decade perfecting spectral scanners that identify resource-rich asteroids from afar, while competitors like Trans-Astra deploy prototype harvesters that use concentrated sunlight to vaporize and capture volatile materials. The economics are staggering. A single 500-meter metallic asteroid could contain more platinum than all Earth's mines have produced in human history. But it's not just about wealth, it's about sustainability. Water ice locked in asteroids becomes rocket fuel when split into hydrogen and oxygen, enabling cosmic gas stations that refuel Mars-bound ships. NASA OSIRIS-REx mission proved the concept by snatching a sample from asteroid Bennu, revealing hydrated clay minerals. Private ventures aim to scale this up, with robots designed to bag entire asteroids in synthetic fabric before processing them in orbit, preventing debris scatter. The technology borrows from terrestrial deep-sea mining and Arctic drilling, but with ingenious space-age twists. Honeybee Robotics' Planet Vac system uses compressed gas to suck regolith like a celestial vacuum cleaner, while off-world's mining bots employ AI to navigate zero-G terrain using tendrils inspired by rock-climbing vines. The real genius lies in their autonomy. These machines must operate light minutes away from Earth-based controllers, making split-second decisions about vane quality or equipment jams. Environmental benefits back home could be profound. Terrestrial mining devastates landscapes and consumes 10% of global energy. Shifting extraction off-world preserves ecosystems while supplying rare earth metals critical for electronics and green tech. Luxembourg, the first nation to legalize asteroid property rights, estimates space mining could eventually supply 40% of Earth's platinum demand without digging a single new pit. Yet the greatest disruption lies in enabling permanent space infrastructure. Lunar bases could source construction materials from nearby asteroids instead of importing them at astronomical cost. Orbital factories might smelt asteroid metals into solar satellites, beaming clean energy to Earth. Even Martian settlers could tap the asteroid belt for phosphorus to fertilize crops or silicon for solar panels. Skeptics cite legal gray areas. The Outer Space Treaty bans national land claims but remains silent on corporate resource extraction. Startups hedge their bets by focusing on use it or lose it models, processing materials in space rather than hauling them home. Others propose sharing profits via space resource dividends, distributing cosmic wealth globally. What makes these robots revolutionary isn't just their drills or AI, it's their role as cosmic pioneers. Like the railroads that opened continents, they're building the supply chains for humanity's next frontier. The age of Earth-bound resources is ending, and the era of celestial prospectors has begun. Hyperspectral imaging satellites are like cosmic detectives, capturing light far beyond what human eyes can see to reveal secrets hidden in plain sight. While regular cameras snap pictures using 3 color channels, red, green, and blue, these advanced sensors split light into hundreds of narrow spectral bands, detecting unique chemical fingerprints invisible to conventional optics. Picture a Martian canyon where ordinary images show only rust-colored rock, but hyperspectral data exposes glistening veins of hydrated minerals, potential evidence of ancient water flows. Or consider how NASA EMIT mission, mounted on the International Space Station, maps mineral dust sources across Earth's deserts by identifying their distinct infrared signatures, information critical for climate modeling. The real game-changer lies in planetary exploration. Traditional rovers must physically traverse landscapes to analyze samples, a slow and risky process. Hyperspectral orbiters can scout entire regions from above, flagging promising sites for further study. The European Space Agency's Mars Trace Gas Orbiter employs this tech to hunt for methane plumes' potential biosignatures in Mars' atmosphere with unprecedented precision. Meanwhile, private firms like Planet Labs deploy constellations of small hyperspectral satellites to monitor crop health on Earth, a capability easily adapted for future lunar or Martian agriculture. What makes these sensors revolutionary isn't just their observational power, it's their diagnostic versatility. Certain minerals absorb specific light wavelengths, creating spectral barcodes that reveal composition without physical contact. NASA's upcoming lunar trailblazer will use this principle to map water ice distribution across the Moon's surface, identifying prime locations for future bases. The same technology could detect organic molecules on Europa's icy crust or pinpoint rare earth deposits in asteroid belts, transforming how we prioritize exploration targets. James Webb's infrared prowess offers a preview of next-generation capabilities. Its spectroscopic instruments identified carbon dioxide in an exoplanet's atmosphere, a feat hyperspectral satellites could replicate across entire planetary surfaces. Imagine telescopes tuned to detect chlorophyll-like pigments on distant worlds or orbital mappers distinguishing between volcanic basalt and sedimentary layers on Venus. The data deluge will require AI assistance. Startups like Orbital Sidekick are training neural networks to instantly classify minerals from spectral data, accelerating discovery timelines. Critics highlight challenges. Processing hyperspectral datasets demands massive computing power, and atmospheric interference can muddy results. Yet innovations like adaptive optics and quantum dot sensors are overcoming these hurdles. The German Aerospace Center's NMAP satellite employs machine learning to compensate for atmospheric distortion, while MIT researchers are developing ultra-compact hyperspectral chips for CubeSats, democratizing access to this transformative tech. The implications stretch beyond science. Mining companies could prospect asteroids from orbit. Environmentalists might track illegal deforestation through canopy chemistry changes, and future colonists may locate underground aquifers by analyzing surface mineral patterns. As these satellites grow more sophisticated, they're not just observing the cosmos, they're giving us X-ray vision to uncover its hidden riches. Imagine building a spacecraft as easily as snapping together plastic bricks. That's the promise of modular design, where standardized components combine like cosmic Lego to create mission-specific vehicles. This isn't just about convenience, it's a fundamental shift in how we construct everything from lunar landers to interstellar probes. Take SpaceX's Starship, designed with interchangeable fuel tanks, cargo bays, and crew modules that can be rearranged like puzzle pieces. Need a satellite deployer? Swap out the habitation module. Planning a Mars cargo run? Stack extra storage units like shipping containers on a freighter. The beauty lies in simplicity. Instead of engineering each spacecraft from scratch, engineers mix and match pre-tested components, slashing development time from years to months. Blue Origin's New Glenn rocket takes this philosophy further with its standardized payload fairings and adapter rings, allowing customers to bolt on their own modules without custom redesigns. Think of it like USB ports for space. Plug in a science lab here, a propulsion bus there, and you've got a functional probe ready for launch. The European Space Agency's upcoming Argonaut lunar lander epitomizes this versatility, offering a base chassis that can host anything from robotic rovers to greenhouse modules depending on mission requirements. Even NASA's Artemis program leans into modularity, with its Lunar Gateway Station assembling like a Tinker toy set in orbit around the Moon. The cost savings are staggering. Traditional spacecraft demand bespoke manufacturing, where even minor changes require costly retooling. Modular systems flip this model, mass-producing components that work across multiple missions. Analysts estimate this approach could reduce spacecraft costs by up to 60%, akin to how Henry Ford's assembly line revolutionized car production. Startups like Atomo Space are pushing the envelope with space tugs, reusable modular vehicles that ferry payloads between orbits. They're swap-out thrusters and power systems tailored for each customer's budget and timeline. But the real innovation lies in upgradability. Picture a Mars-bound module receiving hardware updates en route, new radiation shields or comms arrays delivered by supply drones and installed robotically. Or consider telescope arrays that grow larger over time, adding mirror segments like a coral reef accumulating layers. The International Space Station provided a glimpse of this future with its piecemeal construction over 2 decades. But next-gen modular designs eliminate the need for astronaut spacewalks. Northrop Grumman's mission extension vehicles already demonstrate this, docking with aging satellites to attach fresh propulsion modules and extend their lifespans. Challenges remain, of course. Standardized interfaces must withstand the violent shaking of launch and the extreme temperatures of space without failing. That's where universal docking systems like NASA NDS, the space equivalent of USB-C, come in, providing robust mechanical and electrical connections tested across thousands of simulated missions. Cybersecurity is another frontier. Modular craft could be vulnerable to hacking if malicious components slip into the supply chain. Companies like Loft Orbital address this by rigorously vetting third-party modules before integration, much like smartphone app stores vet developers. What makes this approach truly transformative isn't just efficiency, it's democratization. Smaller nations or universities could afford space missions by purchasing individual modules instead of entire spacecraft. A biology lab in Kenya might contribute a plant growth chamber to a lunar habitat, while a Norwegian team adds an aurora studying sensor pod to a polar orbiting satellite. The International Space Station partnership hinted at this collaborative future, but modular design takes it further, allowing entities without billion-dollar budgets to participate meaningfully in exploration. The implications ripple beyond hardware. Mission planners can now pivot rapidly, reconfiguring a Jupiter probe into a comet chaser if new scientific priorities emerge, or repurposing Earth observation satellites for disaster response overnight. During the 2020 Australian wildfires, modular satellites like those from Planet Labs proved this adaptability, tasking spare camera modules to monitor fire fronts in real time. As private companies and national agencies converge on these standards, we're witnessing the birth of a cosmic industrial revolution, one where spacecraft evolve from handcrafted masterpieces to agile, reconfigurable tools. The future of spaceflight isn't just about reaching new destinations. It's about building the vehicles to get there like children assembling dreams from plastic bricks. Earth's orbit has become a celestial junkyard, cluttered with over 30,000 trackable fragments of space debris, each hurtling around the planet at 10 times the speed of a bullet. From dead satellites to discarded rocket stages, this floating scrap heap poses an existential threat to everything from the International Space Station to next-gen internet constellations. But a new wave of orbital cleanup technologies is turning this crisis into an opportunity, proving that humanity can clean up its cosmic mess before it's too late. Take Japan's groundbreaking magnetic net experiment. Their JAXA agency deployed a 700-meter-long electrodynamic tether designed to slow down debris, causing it to spiral lower until it burns up in the atmosphere. The tether works like a fishing net woven from invisible forces. charged metal strands generate a magnetic field that interacts with Earth's own, creating drag without physical contact. This gentle approach avoids the risk of fragmenting debris further, a critical advantage over mechanical grabs that could accidentally shatter objects into more dangerous shrapnel. Meanwhile, Europe's Remove Debris mission has tested an even wilder concept: harpooning space junk. Picture a refrigerator-sized satellite firing a pneumatic harpoon to skewer a target panel, then reeling it in like a cosmic angler. The same spacecraft also trialed a net capture system and a vision-based navigation AI that identifies tumbling debris, essential tech for future autonomous cleanup drones. These aren't just lab experiments, they're blueprints for an entire orbital sanitation industry. Startups like Asteroid are already commercializing the tech, with their ELSA deservicer demonstrating how magnetic docking plates could turn future satellites into easily recyclable units from day one. The most futuristic solution might be the laser broom. Instead of touching debris at all, ground-based or orbital lasers would fire precise pulses at incoming junk, vaporizing microscopic surface layers to create thrust. Over weeks or months, these gentle nudges would steer debris toward atmospheric re-entry paths. China's Tiangong space station reportedly tested a low-power version in 2021, and the U.S. Air Force Research Lab has studied adapting missile defense lasers for the task. The beauty of this approach, it scales effortlessly. A single laser station could potentially clear hundreds of objects annually without launching a single cleanup satellite. But why does this matter beyond avoiding spectacular collisions? Consider the economics. Every dodged piece of debris saves satellite operators millions in avoidance maneuvers and insurance costs. Mega constellations like Starlink or OneWeb rely on clear orbital highways to prevent chain reaction collisions, a scenario known as Kessler syndrome, where one impact creates thousands of new debris fragments, triggering more collisions in a catastrophic cascade. Insurance firm Lloyd's of London estimates a single major satellite breakup could increase orbital insurance premiums by $200 million overnight, costs that would ultimately trickle down to consumers relying on space-based internet and GPS. The legal landscape is racing to catch up. Current space treaties make no explicit rules about debris removal, creating gray areas around salvaging other nations' defunct hardware. Startups like ClearSpace, contracted by ESA for the first active debris removal mission in 2026, navigate these waters by focusing on cooperative agreements with satellite operators. Their strategy offers end-of-life removal services upfront, like a cosmic towing package bundled with every launch. What makes these cleanup efforts truly revolutionary isn't just the technology, it's the mindset shift. We're transitioning from treating orbit as an infinite dumping ground to recognizing it as a fragile ecosystem requiring stewardship. The same ethos that drives terrestrial recycling and carbon neutrality now extends skyward, with satellites designed for easy disposal and startups monetizing orbital hygiene. Future historians might look back at this era as the moment humanity grew up, not just reaching for the stars, but learning to keep its celestial backyard tidy. Detecting alien life might not require interstellar travel, just an extraordinary telescope and the patience to study starlight. Exoplanet atmosphere analyzers represent the cutting edge of this cosmic detective work, transforming distant pinpricks of light into detailed chemical profiles. Imagine pointing a space telescope at a world light years away and detecting the faint fingerprint of oxygen, methane, or even chlorophyll in its atmosphere, a potential smoking gun for biology. The European Space Agency's Ariel mission, launching in 2029, will do exactly this for 1,000 exoplanets, using infrared spectrometers to dissect the light filtering through their skies. Its prism-like instruments split this light into ultra-fine color bands, revealing which wavelengths get absorbed by atmospheric molecules. Like a forensic analyst reading a wine stain to determine its vintage, Ariel can tell us whether a planet's air contains water vapor, carbon dioxide, or the telltale cocktail of gases that, on Earth, only life produces. NASA's Habitable Worlds Observatory takes the hunt even further. Slated for the 2030s, this telescope will combine a coronagraph, a starlight blocking mask, with spectroscopy sensitive enough to spot city lights on an exoplanet's night side, should any exist. Its design builds on lessons from the James Webb Space Telescope, but with one critical upgrade: the ability to detect ultraviolet light. Why does that matter? Earth's ozone layer absorbs UV radiation, creating a detectable gap in our atmospheric spectrum. Spotting that same signature around another world would suggest not just life, but life protected by its own planetary sunscreen. The real magic lies in interpreting these chemical clues. Oxygen alone doesn't guarantee life. It can form from water molecules split by starlight, but pair it with methane, which sunlight destroys within decades, and you've got a compelling case. On Earth, that combination persists only because life constantly replenishes both gases. Future analyzers might spot even subtler hints. The way plants on Earth reflect near-infrared light creates a red edge in our planet's spectrum. A similar spike in an exoplanet's data could imply alien photosynthesis. The private Breakthrough Listen project has proposed scanning for artificial signatures to industrial pollutants like CFCs or the glow of fusion-powered megacities. Challenges abound, of course. Gas giants like Jupiter mimic some biosignatures through geological processes, while tidally locked planets might concentrate atmospheric gases in misleading patterns. That's why next-gen missions employ spectral triangulation, cross-checking multiple indicators. The LIFE initiative led by ETH Zurich takes this further, planning an array of mid-infrared telescopes that could analyze an exoplanet's atmospheric temperature profile. Imagine detecting the thermal signature of rainforests or oceans from interstellar distances. The implications transcend astronomy. Confirming even microbial life elsewhere would revolutionize biology, offering a second example of how life begins and evolves. Philosophers debate whether discovering aliens would unite or divide humanity, but one thing's certain: these telescopes are our generation's equivalent of Galileo's spyglass, poised to reveal not just new worlds but our place among them. When Ariel first data arrives, we might finally glimpse the answer to a question as old as civilization itself. Are we the universe's sole inhabitants, or merely one whisper in a cosmic chorus of life? Cryogenic sleep pods might sound like something ripped straight from a blockbuster space epic, but the science behind human hibernation is inching closer to reality, and it could completely reshape how we approach long-duration space travel. Picture a Mars-bound spacecraft where astronauts spend months in suspended animation, their heart rate slowed to a few beats per minute, their body temperatures hovering just above freezing. Instead of requiring years' worth of food, water, and living space, the crew would essentially press pause on their biological clocks, waking only when their destination looms in the viewports. The concept isn't as far-fetched as it seems. Nature provides the blueprint. Bears and ground squirrels routinely enter states of torpor, reducing their metabolic rates by up to 95% to survive harsh winters. Scientists at SpaceWorks Enterprises have taken cues from these animals, developing techniques to induce therapeutic hypothermia in humans, a medically controlled state where core temperatures drop to around 32 degrees Celsius, dramatically slowing cellular activity. Their designs for crew pods resemble high-tech hospital beds, complete with intravenous nutrient feeds and automated systems to prevent muscle atrophy through gentle electrical stimulation. Early tests on primates and human trauma patients have shown promise, with subjects revived after days of induced torpor without lasting harm. The implications for interplanetary travel are staggering. A hibernating crew would require only a fraction of the oxygen, food, and water needed for conscious astronauts, slashing mission mass and cost. Radiation exposure, one of the gravest threats during deep space transits, becomes less critical when metabolically suppressed cells are more resistant to cosmic ray damage. Even psychological hurdles ease. Instead of enduring 18 months of isolation in a cramped capsule, astronauts would experience the journey as a single, extended night's sleep. NASA's Innovative Advanced Concepts program has already funded studies exploring how torpor could reduce spacecraft volume by 60%, enabling smaller, lighter vehicles for the same missions. But the real breakthrough lies in the details. Maintaining stasis safely requires solving puzzles like preventing blood clots in near-frozen plasma or avoiding brain cell damage during cooling and rewarming. Companies like Somnus Space are tackling these challenges with biomimetic drugs that mimic hibernation, inducing proteins found in Arctic ground squirrels. Others are developing non-invasive cooling helmets that lower brain temperature without risky whole-body chilling. Meanwhile, the European Space Agency's MELT project is testing whether combining torpor with advanced nutrient gels could allow astronauts to wake periodically for brief exercises, mitigating bone and muscle loss. Critics highlight ethical quandaries. What if a pod malfunctions millions of miles from help? Or how would crews handle emergencies mid-stasis? Engineers counter with redundant monitoring systems and AI caretakers capable of reviving individuals if sensors detect anomalies. There's also the question of long-term effects. While brief medical hypothermia is well studied, months-long torpor remains uncharted territory. That's why initial applications will likely focus on short-duration, top-ups, during solar storm shelters or high-stress maneuvers, gradually building toward full interplanetary hibernation. Beyond Mars, this technology could unlock the outer solar system. Imagine Jupiter's moons explored not by robotic proxies but by human scientists who hibernate through the 5-year transit, arriving fresh and alert. Or generation ships where crews cycle through stasis in shifts, maintaining the vessel across centuries-long voyages to nearby stars. The same science might even revolutionize medicine on Earth, enabling suspended animation for critical trauma patients during transport or preserving organs for transplant. What makes cryogenic sleep so transformative isn't just the resource savings, it's the psychological liberation from deep space's vast timelines. By decoupling human perception from the tedium of cosmic distances, we effectively shrink the solar system. The dream of stepping onto Pluto's icy plains or Saturn's hydrocarbon lakes no longer seems constrained by human frailty, but becomes a question of engineering and will. As research accelerates, the line between science fiction and reality blurs one chilled, measured breath at a time. 19th on our list flips the script on renewable energy. What if we could harvest sunlight where clouds never gather and night never falls? Space-based solar power stations represent this tantalizing possibility, with gigantic orbital arrays capturing unfiltered solar radiation 24/7 before beaming it down to Earth as microwaves or lasers. Unlike terrestrial solar farms hamstrung by weather and daylight cycles, these cosmic power plants would operate at peak efficiency around the clock, potentially delivering 5 to 10 times more energy per square meter than ground installations. Japan's space agency JAXA made headlines in 2023 by successfully transmitting 1.8 kilowatts of power over 50 meters via microwave, enough to boil a kettle, but a critical proof of concept. Their roadmap aims for a 1 gigawatt orbital farm by 2040, capable of powering 500,000 homes continuously. The engineering challenges read like a sci-fi checklist. Kilometer-scale solar arrays must unfold autonomously in orbit, withstand relentless cosmic radiation, and maintain millimeter-perfect alignment to focus energy beams across 36,000 kilometers onto Earth-based Rectinas specialized antennas that convert microwaves back into electricity. Caltech's Space Solar Power project tackled the deployment puzzle with their lightweight prototype that self-assembled in orbit like origami, while China's 2028 plans involve constructing a test station in geosynchronous orbit using robotic assembly techniques perfected on their Chang'e space station. Safety remains paramount. Even low-intensity microwave beams spread over vast areas could interfere with aviation or communications if misaligned. That's why modern designs incorporate automatic shutdown protocols and laser-based alternatives that pose less atmospheric interference. The environmental payoff could rewrite global energy economics. Unlike fossil fuels, space solar produces zero emissions during operation. Unlike nuclear plants, it generates no long-lived radioactive waste. And unlike terrestrial renewables, it doesn't compete for precious farmland or wilderness areas. The European Space Agency estimates that a network of 60 solar satellites could supply Europe's entire electricity demand, with Rectina sites occupying just 5% the area of equivalent ground solar farms. For nations lacking fossil fuel reserves but rich in technical expertise, think Japan or Singapore, this could mean energy independence without the geopolitical baggage of oil pipelines or uranium enrichment. What makes this invention truly visionary isn't just the technology, it's the cascading benefits for both Earth and space infrastructure. The same robotic assembly techniques needed for massive solar arrays would enable orbital factories and space hotels. The high-power microwave transmitters could double as propulsion systems for deep space probes. Even the waste heat from Rectinas might warm greenhouses in polar regions. Skeptics argue launch costs must drop further, but with SpaceX's Starship promising $200 per kilogram fares, the math starts favoring cosmic power. When the first gigawatt streams down from orbit, it won't just light our homes, it'll illuminate a path toward post-scarcity energy, where clean power flows as reliably as sunlight itself. Neuromorphic computing chips don't just process data, they think like a brain, and that could revolutionize how we explore the cosmos. Unlike traditional silicon chips that crunch numbers in rigid sequences, these systems mimic the human nervous system's chaotic elegance, with artificial neurons firing in parallel to handle complex, real-time decisions. Picture a Mars rover encountering a dust storm. Instead of waiting 20 minutes for instructions from Earth, its onboard neuromorphic processor analyzes wind patterns, assesses terrain risks, and reroutes autonomously, all while consuming less power than a light bulb. NASA Jet Propulsion Laboratory has already prototyped this with their brain-scale S2 system, a silicon wafer etched with artificial synapses that learns from its environment like a seasoned astronaut adapting to unexpected challenges. The secret lies in efficiency. Conventional computers waste energy shuttling data between separate memory and processing units, a bottleneck known as the von Neumann bottleneck. Neuromorphic chips collapse this divide, storing and processing information in interconnected nodes that fire only when needed, much like biological neurons. Intel's Loy-Hi processor demonstrates this with spiking neural networks that consume 1,000 times less energy than GPUs when running AI tasks. For space missions where every watt counts, that's the difference between a rover that lasts months and one that operates for decades. The European Space Agency's upcoming Sat-2 satellite will leverage this tech to filter useless cloud cover from Earth observation imagery in real time, saving bandwidth by only transmitting valuable data. But raw efficiency isn't the only breakthrough, its adaptability. Traditional AI requires pre-training on Earth with fixed datasets, leaving probes helpless when facing unanticipated scenarios. Neuromorphic systems learn continuously. JPL's tests show their chips mastering Martian terrain classification by adjusting synaptic weights on the fly, just as a human geologist might refine rock identification skills during fieldwork. Private ventures like Brain Chip are pushing this further with edge learning capabilities, allowing a lunar lander to recognize and avoid newly formed crevices without waiting for software updates from mission control. The implications stretch beyond robotics. Imagine telescope arrays using neuromorphic filters to isolate exoplanet signals from stellar noise instantly, or swarm probes coordinating like a hive mind to map asteroid fields. Deep space missions could carry compact neuromorphic science assistants that prioritize discoveries autonomously, flagging a strange mineral vein or anomalous atmospheric reading without human prompting. Even spacecraft maintenance could benefit. Airbus's experiments show self-repairing satellites diagnosing micrometeorite damage through neural networks that mimic a nervous system's reflexive responses. Challenges remain, of course. Cosmic radiation can disrupt delicate synaptic mappings, requiring error correction algorithms inspired by the brain's own redundancy. And unlike conventional chips, neuromorphic hardware often needs bespoke programming languages, a hurdle companies like SynSense are tackling with drag-and-drop neural design tools. Yet the trajectory is clear when NASA Mars Sample Return mission launches in the 2030s. Its fleets of helicopters and fetch rovers will likely rely on these brain-like processors to navigate, collaborate, and problem-solve without Earth's hand-holding. What makes this invention truly transformative isn't just the technology, it's the philosophical shift. We're moving from commanding machines to empowering them with something akin to intuition. In the icy darkness of Europa's oceans or the methane winds of Titan, future probes won't just follow scripts. They'll perceive, reason, and adapt, carrying not just human tools but synthetic fragments of human cognition into the void. Terraforming Mars might sound like the ultimate science fiction fantasy, but the science behind reshaping an entire planet's environment is grounded in real and increasingly urgent research. Imagine standing on a future Martian plain, breathing air rich with oxygen, watching genetically engineered algae bloom across once barren terrain, transforming rusty deserts into living landscapes over decades or centuries. This isn't just about survival. It's about turning Mars into a second Earth, and the technologies to make it possible are already being tested in labs and extreme environments on our own planet. The first challenge, thickening Mars' wispy atmosphere, currently just 1% as dense as Earth's and incapable of trapping enough heat to sustain liquid water. One radical solution involves importing greenhouse gases not by spaceship, but by jump-starting natural processes. NASA, a planetary science division, has explored bombarding Martian polar ice caps with dark dust or soot to accelerate their sublimation, releasing trapped carbon dioxide and water vapor. The more CO2 enters the atmosphere, the more heat it traps, a feedback loop that could raise temperatures above freezing within decades. Elon Musk famously suggested detonating nuclear bombs over the poles to achieve the same effect, though most scientists prefer less apocalyptic methods, like deploying fleets of automated factories to pump out super-potent fluorocarbon gases, thousands of times more effective than CO2 at trapping heat. Yet warming Mars is only half the battle. Even with a thicker atmosphere, the air would still be unbreathable for humans without oxygen. That's where synthetic biology enters the picture. Researchers at the University of Bremen have engineered strains of cyanobacteria, ancient, resilient microbes that can survive Mars' harsh UV radiation and low pressure while converting CO2 into oxygen through photosynthesis. In controlled experiments, these algae thrived in simulated Martian soil, hinting at a future where vast bioreactors or even open-air algae ponds could slowly replenish the planet's oxygen reserves. The same organisms might also fertilize the soil, breaking down toxic perchlorates into harmless salts while fixing nitrogen for future crops. The timeline for such an undertaking stretches far beyond our lifetimes, likely centuries, but early milestones are already within reach. Private ventures like Mars Terraforming Corporation propose seeding the planet with extremophile lichens and mosses within the next 50 years, creating patches of habitable microenvironments akin to terrestrial oases. These starter ecosystems would focus not on global transformation but on localized habitation zones where pioneers could work outdoors with minimal life support. Meanwhile, orbital mirrors spanning hundreds of kilometers could concentrate sunlight onto targeted regions, speeding up ice melt and photosynthesis cycles. Critics argue the ethics of planetary scale engineering deserve more scrutiny. Should we remake another world in Earth's image, potentially erasing unique Martian geology or however unlikely native microbial life? Legal frameworks are equally murky. The Outer Space Treaty prohibits harmful contamination of celestial bodies but offers no guidance on intentional ecological modification. Some scientists advocate for partial terraforming, thickening the atmosphere enough to allow liquid water and radiation shielding, while preserving Mars' distinctive character. What makes these technologies revolutionary isn't just their ambition, it's their ripple effects back on Earth. The same algae bred for Mars could scrub CO2 from our own overheating atmosphere. Greenhouse gas management tools developed for planetary engineering might help stabilize Earth's climate. Even the psychological impact matters. Knowing humanity holds the tools to reboot a planet's biosphere could shift our perspective from helplessness to agency in facing environmental crises. Terraforming may begin as a survival strategy, but it could end as the ultimate expression of human ingenuity, proof that a species born on one world need not remain bound to it. The dream of walking on a living Mars no longer belongs to fiction. It's a challenge waiting for the next generation of scientists, engineers, and explorers to take up, one carefully calculated step at a time. Breakthrough Starshot isn't just pushing boundaries, it's shattering them with a concept so audacious it redefines what interstellar travel could look like. Picture a fleet of gram-scale probes, each no larger than a postage stamp, hurtling toward Alpha Centauri at 20% the speed of light, their secret. Earth-based lasers blasting 100 gigawatts of focused energy onto ultra-thin light sails, accelerating these nanocraft to velocities no chemical rocket could ever hope to match. Within minutes, they'd surpass the speed of New Horizons. Within days, they'd overtake Voyager 1. And in just over 20 years, they'd reach our nearest stellar neighbor, a journey that would take traditional probes tens of thousands of years. The sheer elegance of this approach lies in its minimalism. Unlike colossal generation ships or warp drives that bend physics to the breaking point, Starshot works with existing principles just scaled to extremes. Each probe packs a smartphone's worth of computing power into a dust-sized payload, cameras with sub-millimeter lenses, atomic-scale spectrometers, and even miniature thrusters for course correction. The sails themselves are engineering marvels, crafted from metamaterials thinner than a wavelength of light, yet capable of withstanding the brutal acceleration equivalent to 20,000 Gs. Early prototypes by the University of Pennsylvania have already demonstrated sail stability under lab conditions, while NASA NIAC program tests laser beaming technologies that could one day form the project's backbone. What makes this invention truly revolutionary isn't just the speed, it's the data pipeline back to Earth. These probes won't carry heavy radio transmitters. Instead, they'll use their sails as mirrors, reflecting picowatt laser signals across the 4.37 light-year gulf to massive receiver arrays on Earth. Decoding these faint whispers will demand quantum leap in signal processing, but teams at the SETI Institute are already developing AI algorithms to tease meaningful images from what would otherwise be noise. Imagine receiving the first high-resolution photo of Proxima Centauri B's surface, its potential oceans, landforms, or even artificial structures, all from a device smaller than your fingertip. Of course, the hurdles are as staggering as the ambition. Interstellar dust becomes deadly shrapnel at these velocities, requiring atomically smooth sail materials that can self-heal microscopic impact. The laser array spanning kilometers must maintain perfect focus over thousands of miles of atmosphere, compensating for turbulence in real time. Even the probe's survival poses puzzles. How will their electronics endure decades of cosmic radiation without shielding? Researchers are exploring radical solutions, from self-annealing graphene circuits to biological microchips based on radiation-resistant tardigrade proteins. Yet the philosophical implications outweigh even the technical ones. Starshot embodies a fundamental shift from send one giant probe to launch thousands of disposable explorers. It's the interplanetary equivalent of dandelion seeds scattered on the wind, a strategy where individual failures matter less than collective success. This redundancy could pay off spectacularly. While some probes might target Alpha Centauri's potentially habitable planets, others could divert to study its binary star's exotic physics or chart the asteroid belts that surely orbit them. The data diversity would dwarf anything a single monolithic mission could provide. Critics question the project's billion-dollar price tag, but consider the alternatives. Traditional interstellar probes would cost trillions and take millennia. Starshot offers a middle path near-term, scalable, and incremental. Phase 1 might target the solar system's edge, testing propulsion and communication with probes reaching Pluto in days rather than years. Later iterations could explore the mysterious Oort cloud or serve as interstellar precursors, paving the way for heavier follow-up missions. The dream here isn't just about reaching another star, it's about proving that interstellar exploration isn't confined to distant futures or fictional warp drives. Within our lifetimes, we might witness the first human-made objects departing the solar system with intent rather than drift. And when those faint laser signals finally trickle back, they won't just carry data, they'll deliver a message to any civilization watching. Humanity has taken its first real step into the galactic ocean. From solar sails skimming on sunlight to self-healing spacecraft that mend themselves like living organisms, these 22 inventions aren't just reshaping space exploration, they're redrawing the boundaries of what humanity dares to imagine. Every breakthrough we've explored, whether it's asteroid mining robots or quantum communication networks, chips away at the notion that the cosmos is somehow beyond our reach. What makes this moment extraordinary isn't just the individual technologies, but how they converge. Picture a future Mars colony powered by space-based solar arrays, supplied by 3D printed habitats grown from Martian soil and connected to Earth via unhackable quantum links. The pieces are no longer science fiction. They're prototypes, patents, and funded missions on drawing boards from Houston to Beijing. The next 10 years will unfold like the golden age of aviation, but for space. Governments and private firms aren't just competing, they're cross-pollinating ideas at a dizzying pace. NASA's Lunar Gateway Station borrows modular designs from commercial space stations. SpaceX's Starship leverages materials science born in university labs. Even traditionally Earth-bound companies like Siemens and Bosch are pivoting to space manufacturing, sensing an industrial revolution brewing beyond our atmosphere. This isn't a zero-sum race to plant flags. It's a collective sprint to build infrastructure that makes the solar system accessible to scientists, entrepreneurs, and eventually families. Yet amid this whirlwind of progress, the most transformative shift might be psychological. For generations, space was the domain of superpowers and billion-dollar budgets. Today, a high schooler can code experiments for the International Space Station via programs like ESA's Cubes in Space. Startups smaller than a local bakery are launching lunar landers. The barrier between us and the stars hasn't just lowered, it's dissolving. So which of these 22 visions resonates with you? Is it the quiet revolution of plasma thrusters, turning interplanetary travel into a sustainable endeavor? Or perhaps the dream of O'Neill cylinders where entire communities spin gracefully in Earth's orbit? Drop your thoughts below. We're at our best when ideas collide. If this journey through tomorrow's technologies sparked your curiosity, hit subscribe for more deep dives into the innovations rewriting humanity's future. The stars have always been our destination, but for the first time in history, the journey feels less like a leap of faith and more like a roadmap we're drafting together. The countdown isn't just ticking for rockets anymore, it's ticking for all of us.